Assalamualaikum and good day everyone. Okay, now we will cover chapter 7, which is combinational logic network. This one still should be covered in the week 6. Okay, so every time you need to follow the course information, the weekly schedule. Okay, here is mentioned chapter 7. Okay, but it's actually covered in in week 6 also. So now you guys can read on your own for more details. I just summarize. So combinational logic networks, Boolean function relates the input with the outputs of digital circuits. In general, each term is implemented using one logic gate. By simplifying and or manipulating the logic expression, the circuit complexity is reduced, thereby increasing reliability and lowering the cost. Okay, instead of using 3 logic gate, you can use 1. So it's a simpler reliability and lowering cost. So in logic circuit designs, we will follow 4 steps. Okay, logic design process. Okay, logic design process, which is conceptualize. Number 1. Number 2, you will go to the truth table. You will design the corresponding truth table. Number 3, you will go for equations. And number 4, you go to the schematic, which is the gate, the design with the gates. Okay, so you can read. I can read for you if you don't want to read it. Okay, so conceptually, to get the bigger picture of overview, you try to visualize the situations, and after that you obtain the truth table from what you have been visualized, and after that you from the truth table you will obtain the simplified Boolean expression for each output. Okay, and we may use Carnot map or Boolean algebra for that. And schematic is the final step where we're going to draw the circuits with the logic gates involved. Okay, so always remember these 4 steps. Okay, now we go for the question. For example, design a majority decider circuits. Okay, what does it mean by this? Okay, for example, if you have a majority of 1 in that variable combination, then your function will result in 1. Okay, for example, if we take a 3 variable situation, okay, if 3 input variable a, b, c, okay, then you do like a box like this because you don't know what happening inside. Okay, what you don't know what is the logic gate involved inside, so you just like this. So you have your a, b, c. So this is majority decider circuits. Okay, at this stage it is the conceptualize. Okay, okay, and this is the resulting functions. Okay, so then you do the corresponding truth table. Okay, truth table. So you have a, b, c as the input variables, and m is your output. Okay, majority decider circuits. Okay, so 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Okay, 1 2 3 4 5 6 7 8. So you see, if there is majority of 1 in the combination, we will have a function of 1. So what does it mean by this? Means you need to have at least two variable having value of 1. And of course, if all 1, you will have all 1. You will have output as 1. So here, this definitely is 0. This one, the 1 is minority, so it's 0. This one, the 1 is still minority because it's only 1. This one, okay, it start to become a majority, so this one is 1. This one, this become the minority again, so it's 0. This one is the majority. This one is majority, and this one certainly is majority. Okay, so you have here, okay, they will produce the function of 1. Okay, now the truth table is shown in table 7.1b. Okay, here. Okay, then we go for the next stage, which is the equations now. Okay, from the equations, we try to obtain the equation from the K-map. Okay, or we try to solve it using Boolean algebra. Okay, so you can have this either one or both of them, up to you, as long as you get the simplified equations. Okay, so let's say I want to use K-map. Okay, so first, of course, you draw the circuits, you draw the table, and you have A, B, C, and you have 0, 1, then 4 possible combination of BC: 0, 0, 0, 1, 1, 1, 1, 0. Okay, you see 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So the rest are 0. Okay, remember the technique to do looping. Okay, it should be covered as much as possible of the cells. It must be the number of 2 to the power of n, and also it must be fewer number as possible. Okay, so here you have, from here you have these combinations, you have this combination, and you have this combination. Okay, so you have 3 loops here. So from the m you can derive, okay, for the first one, for this one, what is the common? The common is what? The common is A. And what is the common for this one? Is the C. Okay, sorry, it's raining outside, but I still want to continue the lecture. I hope you guys can listen to my voice. Okay, and then this one, what is the common? We have this is as the common for this loop. So it is BC. And how about this one? The common is A, and the B is the common. Okay, now we proceed with design the schematic. Okay, we go to the next step, which is the schematic. Okay, so it is simple. You have A, B, C. For this one, you have AC. Okay, this one BC. And this one AB. Then you have or them. Okay, so okay, so it's simple. So this is the equivalent circuit. So because it is raining, I will continue. I'm not sure if you guys can listen. Okay, but I will try. I still want to okay, hopefully you guys still able to listen to my voice. Okay, because I cannot keep on recording in I want to finish one go. Okay, so the next is we want to design okay. So the highlight here, the main point here is actually to design code converter circuits. Okay, code converter circuit. Okay, For example, if we want to design a BCD to ASCII access tree, okay? So you know BCD is actually combinational of 4 bits code, okay? 4 bit. Okay? So therefore our circuit should have 4 input variable, which is A, B, C and D. Okay? So we go for the step 1, which is the conceptualize. So you have 1, 2, 3, 4, and then you have S key. Okay, so it's also 4 outputs. Okay, 4 bit code. Okay, W, X, Y, and Z. Okay, so here is actually BCD to S key access tree converter. Okay, so just as per standard truth table. Okay, the second step, which is, what is the second step? The truth table. So you have A, B, C, D as your input, and as your output you have W, X, Y, and Z. So just put all the possible combination. Make sure it is 15, okay? 16 combinations, okay? So now what you have learned in the previous chapter, how to convert BCD to the access tree, okay? So I won't repeat this. If you don't understand, you can go always refer to the previous lecture, video slides or module. Okay. So I just want to start straight away without wasting the time. So here, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Okay. And you have 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0. This one is 1, 0, 1, 1. This one is 1, 1, 0, 0. And then starting from here, it is a don't care. Okay. So what you can imply by this, you don't consider this input combination because you don't care what is the output there. Okay. And then the next step is we want to obtain the K-map. Okay. So you may refer to here at the module page 80, 80 and 81. Okay. So here, this is showing the K-map for all the outputs. Okay. If you notice, this is the output for W. This is output for X, and this is output for Y, and this output for Z. Okay. What happened for the output of W? You can see, you can take all the one that having one value. Okay. Here. And you may take advantage of don't care to assign as 1 in order to maximize your size of loop. Okay, here. And at x, you have this one. Okay. Then you get your function derived from this is actually w is equals to abc plus a plus bc plus bd, and you can draw the corresponding schematic. Okay, so if anyone don't understand, you can ask me later. Okay, so you can try this at home. Practice makes perfect. Okay. Okay, now we go to the universal gets. Okay, so Boolean algebras, okay, normally involve of n or not get, okay, to produce a circuit design. But real system rarely use this type as the original design. So normally they will use a NAND. Okay, normally this one is a standard operation, but normally they will use NAND and NOR get. Okay, any digital function can be realized using only this or this. Okay, therefore NAND or NOR get are universal get. This one is considered universal get because they can implement any other get. They can produce the function of any other gets. Okay, like or, and, not, and so on. Okay, so the basic of describing this, okay, because we can implement the De Morgan's theorem. Okay, what says in the De Morgan's theorem is that a b bar, for example this, you can break it into some term, then you have a plus b bar. Okay, and also if you have another sum term like a plus b bar like this, you can break it become two small summation as two small products. Okay, and the other way is that you have a bar plus b bar, and you have the big one. Okay, the main inverter. Then you have a plus b bar equals to a b bar, this one. Okay, so this is what is implemented in the NAND or NOR gate. Okay, so we go for the, okay, for example, we want to go for the NAND gate first. Okay, how it's De Morgan is applied. Okay, so let's say for two system with two input variable, so you have this. Okay, then what is in the NAND gate? NAND is actually you have N first, and after that you have NOT. Okay, so you have the NOT N first, and you have the NOT later on. Okay, so let's say for example this is your possible input, let's say, and then you consider the inverted of them. Okay, and then you see is a N and NOT, right? So N, okay, De Morgan's theorem. So 1 1 1 0. Okay, and then this one is actually equals to, they are equivalent. Okay, So how if you want to make it into circuit diagram, I mean schematic. So this is the original, okay, A, B bar, F, okay. This is the NAND gate. This is actually your NOT. This is actually your N, okay. So A, this one is A, B bar, and this one is A bar plus B bar. So you have bubble, okay. Bubble is inverter, and you have OR, okay. Okay. How about the NOR gate? Okay, this is the NAND gate for using the De Morgans. How about the how about the NOR gate? For the De Morgans, okay, how it's actually applied. I hope you guys still manage to listen to my voice, because if the rain is until evening and maybe I don't have much time to record the lecture video, okay, because nighttime is this is fasting month Ramadan, so nighttime I have less time to record my lecture video, okay. So hopefully you guys still can listen to my voice, okay, despite the rain outside. Okay, so how about the NOR gate then? The NOR gate, we will consider this, okay. Okay, the same thing, A, B, possible input combination, okay. And then you have you invert them to see the possible value. Okay, and then for the NOR gate, okay, to have 1 0 0 0, okay. This concept, I think you guys need to understand which you need to understand the NOR gate operation, okay. The NOR gate operation, you need to understand, you refer to the previous lecture, okay, how it will be 1, how it will be 0. For is it the input is the same, output is not, I mean input combination is the same, input combination is different, please refer to the previous lecture video, okay, for NAND and NOR. I won't repeat here, okay. Then after that you have from here, for the De Morgan's theorem, for A plus B bar here, here is equivalent to A, B, okay. So they are equivalent, okay. This one you can try at home, okay. This is how you actually manage to get the derived NOR and OR function just using NAND gate, okay. So continue with these things, okay. So for the first, this F equals to A plus B bar, then you have F here is A dot B bar, okay. This one is simple, the circuit is actually, this one is also, you have A, B, then A plus B bar, A plus B is OR, then you have the inverted, okay. How about this one? You have A and B bar, and you have them as inverted. Okay, then you have N. Okay, so you guys can see this. Okay, how we actually able to derive NOT and OR using just a NOR gate. Okay, simple. Okay, if you don't understand, we can discuss again. Okay, but this one is pretty much the understandable. Then this one is the XOR gate constructed using only NAND gate. You can try to do the proving yourself. Okay, and to see this circuit is correct or not, right? Based on the XOR operation. So so this one is the NAND networks. Okay, NAND networks. So discuss how complete logic network may be built using only NAND. Mean you don't use any other gate, you only use NAND gates. Okay, a similar technique may be followed to build network based only on NOR gates. Okay, like you guys know already, the universal gate can be NAND or NOR. Okay, it should be noted that only AND or OR function need to be converted to NAND or NOR. Okay, you see, AND or OR. Why it says like this? Because for example, if you have the N, for example, okay, you want to simplify the circuit, so you can actually introduce two bubble. This one we cancel out each other, right? Means there's no effect of, but there's no effect of having two bubble here because they bar we still revert back to the same value, just like A bar double bar, it become A again. Okay, so here what happened is that this why is mentioned that only AND and OR function need to be converted to NAND or NOR gate. Okay, only these two they can be converted. Okay, AND and OR. So here what happened, you will move the bubble through here. Okay, each of them, so you will have okay, simple. And the movement of the bubble, okay, the bubble is the inverter, need to be followed. Okay, the rule. Okay, for example, this one, if you want to push the bubble to the right, okay, here if you want to push, it will pass through two routes, so you should have bubble at each side. Okay, how about if you want to pushing the bubble to the left, here if it's go down, it like this, just like a river. Okay, so I think it's understandable. Now construct the circuit for field F equals to AB plus BC using only NAND and not gates. So the instruction, the exercise that construct F equals to AB plus BC bar using only NAND and not gate. Okay, only NAND and not gate. So this one is simple. First, you need to do the three variable, foreseeable variable A, B, C. Okay, then you have AB passing through the N, and then you have BC. BC, BC. Okay, B and C, because it's bar. And is going to the OR function. Okay, so simple. Oops, I dropped down my things. Okay, never mind, ignore that. Okay, so what we can actually do, we can introduce, just like I told you guys, we can introduce bubbles. Okay, then bubbles we go to here, each of them, then you will have this one. Okay, so finish. So this is NAND and NOT gates. Okay, so I think it's quite simple. You guys can try this at home. Construct the circuit AB plus C using only NAND and not GATE. Okay, and you may try this example as well. Okay, this is video, so it's easy for you guys to, for those that not having module, okay, you can just pause and you try this at home. Okay, the next I will cover on the mixed logic and also 7.5 NAND gate integrated circuits. Okay, so you guys can try the exercise, okay, the related one. Okay, don't wait for me to give you to submit to me in the forum. Okay, just try what you guys can. Okay, the one that not cover, you don't have to try. Okay, you can try later on because I not yet covered. And avoid to ask me question in advance because it's good for you to do advanced study, but I cannot like try to catch you while I'm not teaching that subject yet. Okay, it's not that I don't know the answer. Okay, it's just that I want to be just follow the flow. Okay, so thank you. Assalamualaikum warahmatullahi wabarakatuh, and see you guys again.